Okay, so we were discussing, so important announcement, quiz 3 is up, quiz 4 is up. The assignment 4 will be up probably by the end of this week. There's no class on Thursday. And the next class is going to be next week on Tuesday. Okay, so we are talking about eigenvalue assignment. Today we are going to talk about two topics. One is how do you assign eigenvalues in a multi-input system. So your B matrix doesn't have a single column, it has multiple columns. How do we do the eigenvalue assignment? And then when your V has multiple columns, then you can also do what is known as eigenvector assignment. And so we want to study the theory of eigenvector assignment as well today. So there's a lot of matrix algebra that we'll be doing on the board. But I wanted to show you at the beginning of the class what exactly is this eigenvector assignment thing about. Okay, so this is a vehicle. It has one vehicle has no active suspension, the other vehicle has an active suspension, and the eigenvector assignment is going to show you what happens when you design your active suspension in order to cancel or have certain class of eigenvectors in your vehicle. They don't call it eigenvector assignment and stuff, and I didn't find a definitive reference where you can actually study how suspension systems are designed to do this eigenvector assignment. But it seems to me that that's exactly what they are doing when they talk about this technology. But I could be wrong. But it nonetheless shows you the power of feedback control systems in the context of a luxury vehicle.
A revolutionary electromagnetic suspension system that would offer an incredibly smooth ride for cars. The secret project is called Project Sound. You should be able to build a car that's basically flying along the ground, stay level all the time. So when you get to the bumpy road, you can stay level, and you turn brake, you can stay level. When we started the project, we actually started with electric command.
You see, these are the modes. These are the modes of the
This is the unmodified
system.
That's what we're starting. And it's going to come down at a good rate of speed, and it's going to make a hard turn, lane change, and then we're going to do a very hard braking maneuver. Then it'll come over these bumps, and then it'll slalom back. So now the white.
Perfect. So now, when you looked at this video, you saw how the car was moving in different directions as it was turning. So that's the eigenvector of certain modes of the system and of the feedback system. So A plus BK, that's the eigen. So they have picked a K matrix for this particular vehicle, and it's giving you A plus BK, which is the feedback, the dynamics of the feedback system. And the way the car is moving is essentially eigenvectors corresponding to it has some relation with the eigenvectors and the modes of the system associated with the A plus BK matrix. The other thing that I want you to notice in these videos is how quickly this car comes to a stop. I mean, the oscillations come to a stop. So let's look at this video once more.
Come down at a good rate of speed, and it's going to make a hard turn, lane change, and then we're going to do a very hard brake.
It was vibrating, it was going up and down. This vehicle was going up and down, right, at the time it stopped. And so you see how quickly that vehicle's oscillations damped out. And that's essentially what's the real part of the eigenvalues of that particular A plus BK matrix. So it's an indicator of that. So if the real part is close to the origin, then in that, if the eigenvalues are close to the origin, then it takes a long time to damp out the oscillations. If the eigenvalues are far away from the origin, the oscillation gets damped out very quickly.
Then it'll come over these bumps, and then it'll slalom back. So now the white car, same make, same model, same everything, except completely modified suspension system.
So cool. I don't have this car, but I wish I had this car.
One after the other at a fairly slow clip. And I just want to ask about it. To finish the demo, Bose gives us a look at a springy feature it had no intention of putting into a passenger vehicle, but it's a fun way to show off how high-tech and powerful the suspension system is. Our visual sensor doesn't make sense to that.
It's funny. Right after we did it the very first time, I remember a person asking.
I'm not sure what the relevance for that is, but anyways, I think you got the idea that the eigenvalue assignment is very important, especially for things like this, suspension systems like these. You have similar problems in satellite because you want to make sure that you control the vibrations in the satellite. You have problems in flight, you want to control the vibrations in the flight, and you want to decouple certain modes of operations in the flight. So all of those are kind of stuff that we are talking about today.
It's kind of like the question, what do they use the same discussion in dot car cars?
Sorry?
Rally cars using desert.
Which car?
Rally cars using desert dot car, I think. The racing.
Okay.
Do they use that?
I didn't get your question. Can you explain? Yeah.
It is an irrelevant question, but I was just wondering.
About what? I didn't understand your question.
There's this dot car racing desert. It's a rally in desert view. So.
Okay, maybe yeah, maybe I don't know. I am not very sure, but this active, I know that Porsche is selling active suspension system in some of their high-end models. I know that Mercedes is working on active suspension systems as well. I'm not sure if the older cars have it, but definitely the newer cars should have it. And this is the same Bose as the music system Bose. So they actually build the suspension system as well. I don't know what the connection between music and suspension system is, but I believe it has something to do with linear systems theory. So, okay. So we'll get started with the pole placement or eigenvalue placement of A plus BK. So do I need to recall what we did? Okay, let's x dot t equals to axt plus put. So we are not worried about the observability right now. So this is my linear system. I want my ut to be of the form I'm pretty sure it is plus f. F of xt, my reference signal is 0 right now. So it's just f of xt. And I want to find f. The goal is find f such that a plus bf lambda I equals to lambda I. This would be my first problem statement for today. And then find f such that lambda I a plus bf equals to lambda I and a plus bf vi equals to lambda I vi. So this is eigenvector placement as well. So not only I'm doing eigenvalue placement, but I'm also doing eigenvector placement. So we studied the first problem in the previous class when B was just a one-dimensional, I mean, it had one column. Today, I have m columns in the B matrix. So B is in Rn cross m. So when m was equal to 1, we did that in the previous lecture, and it was actually very easy to find the form of f. You generally cannot do eigenvector assignment in that case because you don't have enough degrees of freedom. But when you have m different vectors, then you have enough degree of freedom to be able to do something more interesting. In vehicles, for instance, the kind of vehicles you saw in the video, they had 4 different active suspension system, one attached to each wheel. As a result of which, this was 4-dimensional matrix. I'm not sure if it was more than 4. I mean, a lot of these things are sort of internal information of the company, so they won't share it with other people. But I can only guess by watching the video that this probably is a 4. I mean, there are 4 different actuators, so this M is equal to 4 in that particular vehicle. Okay, so what should our strategy for this, for solving the first problem, should be? So we want to convert this into the typical controllable, what is that, companion form. Yeah. So I'm going to make the assumption that AB is controllable. So we talked also in the previous class about, if you convert this, if you do a similarity transformation of the original matrix, then how do you pull the solution for the controllable form back into the original form? So I think that's something you can definitely do. So we'll try to do a similarity transformation and we get it in the controllable companion form. So that form actually looks something like this. I'm going back in the book now. I'm talking from page 256 to 258 in the book. Okay. So I'm going to define, so I want to convert this into, I want to do a similarity transformation and I want to convert it into a controllable companion form. So I'm talking a little bit about the theory of how to do the controllable companion form for this class of systems. So do a similarity transformation to get controllable companion form. The entire procedure is laid out in the book in 256 to 258. So I'm just going to pick the most important elements from those pages. You can definitely go back and read specific matrices that they have constructed in order to convert this into the controllable companion form. I'm not going to go into those construction, but I will talk about what the implication for our situation is going to be. Okay, so I'm going to define mu I to be max of 1 to n such that bi, abi, a raised to k minus 1 bi are linearly independent. Sigma k to be summation mu I equals 1 to k. And the fact is, summation of mu I is equal to n. I equals 1 to n. One note I wanted to make here, I think the book is not very clear on that topic, but I wanted to make sure you are aware of it when you read the book. Generally speaking, you don't have to, you might be able to get n linearly independent. So remember, these are all the columns of the controllability matrix. So C is B, A, B, A raised to n minus 1 B. And essentially the elements of this matrix is essentially the vectors that you see here. And so as soon as you reach the n linearly independent vectors, you are supposed to stop. And so in some sense, the summation of mu I, as I've defined it here, could be greater than n, but you have to stop. You have to stop taking further vectors after you have reached n linearly independent vectors. So what I mean is, I'm going to replace this with so we'll have to collect all the vectors that are linearly independent from here. Then I have to collect all the vectors that are linearly independent from here. And then I have to stop as soon as I reach n linearly independent vectors. And so then I just have to focus on those elements of the B matrix, and I can ignore the other elements of the B matrix because other elements don't really improve the controllability. They just the system still remains controllable with just let's say B1 and B2. So you have mu1 number of elements from here, mu2 number of elements from here, mu1 plus mu2 equals to n. You don't need B3, B4, B5 and so on, because just with B1 and B2 the system is controllable. So everything else is just adding more redundancy into the system, but it doesn't really improve the controllability of the system. To give you an example, how many of you know that passenger jets can fly and land with just one engine on? How many of you know this fact? Few people? Okay. So we have two jets, we have two engines in every passenger plane, two or more engines, sometimes you have four engines. But generally speaking, passenger jets are designed in a way that with just one engine on, they are still controllable. So the additional engine that they have is purely for redundancy purposes. Okay, it's not important for controllability of the flight itself. So in those cases, you will be in a situation where you just stop here because B1 to A raised to n minus 1, B1, these are controllable and you don't need any of this stuff, right? So those are also so when you are coming up with general theory, you have to be careful about all of these things. I'm not so careful about it in the class, and the book is also not very, book mentions it, but I think I would have much preferred that the book made it very clear about how exactly to do it when you have multiple redundancies in the B matrix. But anyways, what I want to focus on here is that you are only collecting a certain number of B's so that you have n linearly independent vectors and no more, right? And so in that situation, if you sum all these mu i's, you will get, they will all sum to be equal to n. Just something to keep in mind. Okay. Perfect. So by extracting these linearly independent vectors from here, you can, and by massaging those vectors a little bit, you can construct a P matrix, which will be giving you the similarity transformation. And so you arrive at the following matrix structure. So this is the controllable companion structure. So AC is PAP inverse. BC is PB. AC equals to AIJ. BC equals to BC1 BCM. I want to say something about these AC and BC. Let me give you I don't think I want to give you the form of this, but I think there is an alternate way to write AC and BC, and I want to focus on that. So I'm going to define A bar C. So this is given, the expressions for these matrices are given in equation 6.54. So if you are interested, you can take a look at it. I don't want to write those complicated matrices in the class, but there is an important upshot. You can do a little bit more massaging in order to get A bar C to be diagonal of A11 A bar MM, B bar C equals to diagonal of B bar 1 B bar M. A bar II is equal to 0 I mu I minus 1 0 0. And there exists matrix AM and BM okay, such that AC equals to A bar C plus B bar C AM. And this is the part that I want to note here. And that's all I need. I don't need anything else from this particular part of the book. So I guess I'll let you guys write and then I'll go over this once more. Okay. So what did we do? We have AB, which is controllable. I want to put this in an appropriate format so that I can start building controllers so that this particular condition is satisfied. So what I'm going to do is I'm going to build a controller for the canonical, the controllable companion form, because it's much easier to design the controller for the companion form. So then I need to talk about the companion form. So there is a way, there is a structure that you need to follow in order to get to the companion form. And the companion form actually satisfies this matrix condition. There exist matrices AM and BM such that the companion form matrix AC and BC can be given with this particular structure. And that's the structure that I'm looking for that helps me compute the uh, controller F. So let me do that. So I have AC equals to A bar C plus B bar C AM, and BC equals to B bar C BM. One thing I want to note here is that BM is actually a square matrix. So AM is not a square matrix, but BM is actually a square matrix, and typically it's going to be an invertible matrix. Some of this is by construction, it's going to be an invertible matrix. Okay, any questions so far on this particular topic? So I did, this is my PAP inverse and this is my PB. So this is PAP inverse, this is P times B. Okay, now that I got this companion form matrices AC and BC, I want to be able to find the eigenvalues. So I want to find, so Q1 prime. So this was my Q1, this is my ultimate goal, but right now I'm going to change the goal slightly. So this is my Q1 prime, which is find FC such that AC plus BC FC, the ith eigenvalue is equal to lambda I. Right? Because this would be a similarity transformation of this matrix, so the eigenvalues will not get changed. Okay, so let's look at this. My A, C, F is given by AC plus BCFC. My AC is written here, so that's A bar C plus B bar C AM plus BC is B bar C BM FC. Oh, I see something common here. So I have A bar C plus B bar C AM plus B bar C BM. So this is what my closed loop system, this is what the system matrix of the closed loop system in the controllable companion form is going to look like. Okay, what should I do next? I want the eigenvalues of this matrix to be this. Okay, so that's my question right now to you. I want the eigenvalues of this matrix to be exactly this lambda I that I had picked here. So what would you do now? Any ideas? Yeah, what do you want to?
The equation is a VC, VM FC, or it can PM.
Oh, I see. Oh, that's right. That's right. Thank you. You're right. Perfect. I want my AD. So one nice. Everyone remembers the matrix AD from the previous lecture? No, I know many of you were not there. So let me remind you what. So desired characteristic polynomial was given by alpha d of s minus maybe alpha d of lambda, lambda minus lambda 1, lambda minus lambda n, which is given by so dn minus 1 to d0 are the coefficient, and I have a desired closed loop matrix So the characteristic polynomial, it's well known. It's easy to see, easy to show that characteristic polynomial Okay, so we want this ACF to be the same as AD. So I want ACF to be the same as AD. So I need to find an FC which can help me get this particular form. So the book suggests that I can pick FC to be Bm inverse A dm minus am, and ADM is given by where can I write it? E sigma m minus 1 transpose minus T0 minus T1 minus dn minus 1. So ADM is given by this matrix, this AM is given by this matrix. Okay. So this is a way, this is an algorithm, or this is a structured way of computing the gain matrix FC for the controllable companion form, so that the eigenvalues of the closed loop system of the controllable companion form is equal to lambda I. So you can either do this, or you can just call a Python command called signal.place_poles, and that will do it for you. It'll lead you to the same final answer, but Python has a package. I'm pretty sure MATLAB has a package. So what you give that command is the A matrix, the B matrix, and the lambda i's that you want, and it will do all this computation. All of this stuff will happen internally in that package, and it'll give you the final F that is going to solve the problem. And F is going to be FC P inverse. So once I find my FC, I can do FC P inverse, I get the value of S. Okay. So that's the approach for doing just the eigenvalue placement. So I have picked some eigenvalues. I have multiple degrees of freedom in my system. I have multiple actuators in my system. So I can actually place the eigenvalue wherever I want to for this feedback system. And if you have disturbance in the system, the eigenvalues, the real part of the eigenvalues, will determine how quickly that disturbance is going to die out within that system. Okay, any questions on this part? I think the approach is, what I want to take away is not the specific mechanics, because I know that there is a Python package which does that for you, but the approach, because when you call the Python package and it makes a mistake, you should be able to troubleshoot it. And so this is the procedure through which the Python package figures out what the F matrix is going to look like. And so if in case you are encountering an issue in the future, you know exactly what the algorithm behind that signal.place_poles is going to be. So this is the logic. Convert the original system into controllable companion form. Use the controllable companion form to find the FC, and then pull the FC back into the original system using this P inverse. Remember, this P was determined for getting the controllable companion form. So So you use this in order to compute the value of f, and that f solves the problem number 1. Okay. Now we are in the more interesting territory. We not only want to place the eigenvalues, but we also want to place the eigenvectors. So can someone do a back of the envelope calculation and tell me if all eigenvectors can be placed or not using this matrix F? Can you guys figure this out? Like, I want to be able to compute this matrix F so that I can place all the eigenvalues and the eigenvectors. Is it feasible? Is it not feasible? Under what conditions would it be feasible? Can anyone think about it while I erase the board? Okay, so let's consider the following situation. I have only one actuator, so I only have one vector here. My f is n dimensional. No, not yeah. It's n dimensional. It's 1 cross n vector. Right. It's 1 cross n vector. In that case, and I have n independent variables. I have n eigenvalues to place. And how many eigenvectors? What's the size of the eigenvectors? N cross n, n square. So I have n square eigenvectors to place. So I have n plus n square variables to place. But I have only n variables here, right? So I guess it sounds unreasonable to be able to place n square plus n variables using just n values of f. So it's not always feasible. Okay, that's the upshot. It's not feasible to pick all the eigenvalues and all the eigenvectors. So you always have to make some choices. Generally speaking, it's more important to pick the eigenvalue, less important to pick the eigenvectors. But of course, for safety constraints, or if you are manufacturing a luxury vehicle or something like that, something you want to sell for $100,000, then VI also needs to be managed. And then you have to buy appropriate actuators to be able to do that. So the question is, question 2 prime, under what conditions can I do both? What I mean is I want to do eigenvalue placement and eigenvector placement as well. So let's think about it. I want lambda I to be my eigenvalue and I want Vi to be my eigenvector. This is coming in assignment 4, by the way. I'm asking you to design a controller that has a specific eigenvalue and eigenvectors as well. So you will see how and why this should be done in a specific situation. So I have lambda I minus A plus Vf, this multiplied by Vi is equal to 0. This is what I want, right? I can equivalently write this as lambda I minus A B VI. Okay, so this will be true if and only if this is true. Awesome. What do you think is this particular vector? So this is a vector, this is in Rn plus m, I think. This is a vector in Rn plus m. What do you think this vector satisfies? Anyone has an idea what does this vector satisfy? Vi and minus fvi. It's in the null space of this matrix. Lambda is something that I have picked. A and B is something that's given to me. So I constructed a matrix based on what I picked, what's given to me, and I want this eigenvector and this minus fvi to be in the null space of that particular matrix. So my vi and minus fvi belongs to the null space of lambda I minus A and B. Whenever we see a null space, we know that it's a subspace in Rn. If it's a subspace in Rn, then there must be linearly independent vector that spans the entire subspace. If there are linearly independent vectors, I can always stack them into a matrix. And so let's say my matrix, the basis vectors for the null space is, let mi minus di be the basis vectors. It's actually a matrix. It's a matrix of basis vectors. And then, yes.
I was going to say, to clarify, that you would basically just go through each I and
Yes.
generate. So that would, like, if you had n like nodes, equal modes you're aiming for, you would do that n times.
You will do that n times.
Okay.
Yeah. You will find out what the basis vectors are going to be for the null space of lambda 1 I minus AB, lambda 2 I minus AB, and so on and so forth. And you will construct all these matrices n times. Okay. So each column of this matrix is a basis vector for the null space of this particular matrix. And so what happens is, if this vector lies in the null space, then there exists aj in I don't know what the dimension, that's the dimension of the null space. So this would be R dimension null space such that Vj minus Vi minus Fvi equals to Mi minus Di Ai. Oh, this should be Ai. Let's unpack this even further. Okay, so I see some similarity here. So this Vi appears here, so that's mi times ai, and then that vi appears here as well. So what I get is vi equals to mi ai and minus f vi equals to minus f mi ai equals to minus di ai, or f mi ai equals to di ai. So I have this expression and I have this expression. Okay, so if I want to pick the eigenvalue as well as the eigenvector, then by some logic, it seems to me that these two conditions must be satisfied. If these conditions are not satisfied, there is no way in hell I'll be able to do the eigenvector placement as well. And it turns out it's an if and only if condition. So this is theorem 9.12 in the book. Where should I write it? Let me erase this part. Everybody has noted this part. I'll wait for a few more minutes. Some people are still writing. Okay, so let me erase this. So theorem 9.12 in the book, lambda I vi is eigenvalue eigenvector pair of A plus Pf if and only if there exists AI such that AI not equal to 0. Okay, that's the important result. And actually, we have already proved the forward direction, and the reverse direction is sort of straightforward by using the definition. So the proof is done, and this one is follows from matrix algebra. Essentially, you backtrack the same set of steps and then you end up proving the reverse statement as well. There isn't much to be done for proving the reverse statement, and the forward statement is exactly the argument that we made earlier. So that gives you a fundamental limitation on what eigenvalue eigenvectors you can place in the system. Generally speaking, in a very complicated system, you would want to place all the eigenvalues, but only a few eigenvectors, because those are the most important eigenvectors. And so you will have to do some massaging of this whole structure so that you find a specific f that actually solves the problem, that does the placement for the specific eigenvalues and eigenvectors. Okay. Generally speaking, the placement of eigenvector is more of a business decision. The placement of eigenvalue is sort of a legal decision. You want your system to be stable, you want it to satisfy some performance specification. But this VI is something that is a business decision, whether you want to place the eigenvector or not. If you are building a $20,000 car, you don't want to go through the pain of placing the eigenvectors, but if you're building a $100,000 car, then you want to go through the pain. And if you're building a $100 million rocket, you definitely want to put that effort in and make sure that the eigenvectors are reasonable. A lot of the stuff was built in the 1970s and 80s when the computers were not that available. So all of this was supposed to be done by hand. But nowadays, you have Python packages that can do that. Any questions so far? Okay. So we talked about what you would have done if you were born in 1990s. Well, not born, if you were doing research in 1990s. I guess you are all born in 1990s. So what would you be doing if you were doing research in 1990s? You would try to identify whether you can do this eigenvector placement for a rocket, for an airplane, for a suspension system of a vehicle, and things like that. Okay. So what's the more modern technique? So modern technique is maybe like beyond something that started in 1990s and then became quite commonplace in 2000s and 2010. The idea in more modern system is to not worry so much about the eigenvalues and eigenvectors. I mean, those are important. But let's convert all of this into an optimization problem and solve the optimization problem. Now, of course, this class is not a class on optimization. So I can't go through the derivation of what the control strategy, how do you derive the control strategy that is optimal, because I need to then introduce dynamic programming and so on, which is already done as part of 5500, and I know some of you have taken it. But I want to cover what the controller form looks like if in case you wanted to use optimization in order to design the controller. So the goal now, I'm going to change the goal slightly for the next 20 minutes, which is I have this linear system, I have this form of controller that I want to compute, and I have all this controllability and all that stuff satisfied. And I want to be able to figure out the controller for a specific performance index. Okay, so let me write down what that is. Okay, maybe I want you guys to think about it. The following. So if you have an optimization problem that you need to solve versus doing some of this using some of this technique to come up with the function f, from an applications viewpoint, what changes? How does things change if you have an optimization problem to solve versus if you just want to pick f? And you have some thoughts? Yeah.
I mean, I always considered, like, I guess one of the ones that I know a little bit about is LQR.
Mm-hmm.
So I considered, like, LQR would be if I could build the system completely from scratch and design it, I could determine, like, how much I wanted each actuator to move
Mm-hmm.
and weigh it based off that. Versus, like, the eigenvalue, eigenvector would be if I was just looking at external performance. If that makes sense.
Okay, good point. Okay. I wasn't thinking along that direction, but yeah, that would be one way to think about it. So you are more interested in, so LQR, so that's what my objective is. The goal 3 is find f such that f minimizes integral 0 to capital T xt transpose m transpose q m xt plus ut transpose r ut dt. So this is my performance index. This will be my LQR problem. But my f is supposed to minimize this performance index, and if you want ut to be high or low, then it gets optimized accordingly by employing the right set of tools, right set of optimization tools to solve this problem. Anything else that comes to mind? You know, the way I think about it is as follows. Once you pick, so in the traditional systems, if you go back to 1970s and 80s, once you design this f, the f remains on the system for the rest of the life of the system. I built a transformer. This transformer is going to be in service for the next 50 years. And whatever f I have designed for that transformer is not going to change. I mean, that f is not going to change for the next 50 years. Okay, no matter what happens to the transformer. In the middle, like at the end of 20 years, you might go and change some fluid in the transformer. At the end of 30 years, you might go and, I don't know, add a new paint on the transformer or whatever, right? So you keep doing repairs of the transformer, but you're not actually changing the transformer itself. Yeah.
That is for the model systems to design an adaptive kind of that.
We are not talking about adaptive control, so that certainly was one of the considerations back in 1980s and so on. But we don't really have any. I need to be careful. Most control systems that you see today are still using non-adaptive controller. But ideally, it would be nice if we had adaptive controller. But I think the applications are not there yet. The theory is there, but the applications are not there yet. Okay, good point. So that was the traditional approach. Then people said, okay, you know, this one f for the rest of the life doesn't really sound very nice. So how about we change f depending on some situation, like, you know, some sensor turned on, some reading went off. So I'm going to change the value of f. And so that's called a switched system. So you switch the controller depending on what the state what kind of states you are observing right now is, but you still remain within the realm of linear controllers. What changes when you have LQR type of controllers is now you have Q and R matrices, and you now need to have microcontrollers that can do the computation, can do the optimization, and figure out what the optimal value of f is going to be. So it's not like you solve for f at the very beginning of time and then you forget it. You can actually keep changing the value of f depending on the M, Q, and R matrices that characterizes the cost, the performance index of the system, and by changing the, like, if you have A and B matrix and you have M, Q, and R matrix, then you can compute f using a microcontroller on the device, and then you can use that device to keep doing optimization and keep updating the value of f depending on what the current A, B, M, Q, and R matrices look like. Okay, so that's the idea. So earlier it was hard coded. Now you can put a microcontrollers in. Microcontrollers are very cheap. It costs $1, $2, $10, whatever. You can put that $10 device, and you can keep updating the system accordingly, the controller of the system accordingly. Yes, please.
And you say that's the operating system parameters, but that's adaptable instead of an point of control.
Okay, very good question. So the question that he's asking is, would that be adaptive control if f is changing as a function of A, B, Q, and R matrices? Is that adaptive control? Yes and no. So what adaptive control does is you have this A and B matrix at the very beginning, and you look at the error between what you expected and what you actually see on the ground, and you use that error to drive the value of f. So in some sense, adaptive control is not necessarily doing what is known as system identification. I mean, it could be doing system identification also, but it's essentially using the error between what you actually see on the ground versus what you had expected. If this was true, use that error signal in order to drive the value of f. So that's adaptive control. Reinforcement learning is sort of the modern version of adaptive control, okay, which also tries to do the same thing. And I've taught a course in reinforcement learning last semester, which I know some of you had taken. So reinforcement learning also is a class of adaptive control techniques, and then there is a lot that is happening in reinforcement learning. Anyways, I don't want to get into that. So now the question is, where did this thing come from? So, okay, so let's say I want to trade off. So the reason for this performance index is that I want to trade off the strength norm of mxt. I don't really want to use the norm. Trade-off. I want to say the amplitude, but I'm not able to figure out what would be the right way to talk about the amplitude of a signal. So xt is my original state, m is a matrix, I'm multiplying x with m. And this has some amplitude, and I want to trade off the amplitude. Okay, let me just write amplitude. mxt with control effort. ut. So I have a linear system, I have a performance index. What I generally see is that if I put in a lot of control effort, if my ut is extremely high, I can drive xt to 0 very quickly. On the other hand, if my control effort is low, if my ut is very low, then my m of xt is going to be high for a very long period of time. So the question then becomes, how do you trade off these two things? So you always have this trade-off, you always have to make this trade-off because you have actuator saturation. So there's only so much of control effort you can apply on the vehicle, I mean on the control system. So to give you an example, I recently changed the tires on my vehicles, and what I was told is in the spec sheet of the tires that if I'm driving at 60 miles an hour, it's going to take me 180 feet to come to a complete stop. Okay, that's the maximum control effort that I can make. I had options of buying more expensive tires, like a $400 per tire kind of tire, and that could stop in 90 feet or 100 feet. Okay, so that had that capability. So if you think about it, there is a natural trade-off between what m of xt is going to look like, which is the velocity in my vehicle's case, and the control effort. And no matter how hard I press the brake, I'll still take 180 feet. So right now, the tires that I have on my vehicle, no matter how hard I press the brake, it's going to take me 180 feet to come to a complete stop. Okay, so I have made that trade-off for my vehicle, and every time you go to buy tires, you will be bombarded with all of this information, and you'll have to make that trade-off for your vehicle as well. Okay, so this was the idea, and so people said, okay, I have a linear system, and I want to trade off the amplitude with the control effort, both of which are measured by the absolute value of the magnitude of what you are xt, m of xt is going to be like, and ut is going to be like. So what they did was they came up with a quadratic function. So I pick q to be positive semi-definite matrix, I pick r to be a positive definite matrix, and and then my one part of the cost is this is one part of the cost. This is the cost of state, and then you have a cost of control, which is UT transpose RUT, and then you add the two costs and then you integrate it, and that's how you get to this particular expression. So I'm going to add the two costs and I'm going to apply dynamic programming. And this is covered in ECE 5500 in discrete time and ECE 8250. I think it is 8250, but I could be wrong. But it's called optimal control, and it's taught in that particular class as well. That's the continuous time version. And so without going into the derivation, here is what the solution is going to look like. So my mu star xt is going to be fxt, which is minus R inverse B transpose Bt P star T xt, and P star T satisfies d over dt P star T So we want AB stabilizable. Okay. If AB stabilizable, no. A q raised to half m detectable, then P star T converges to PC. So as T goes to infinity, if under some conditions this particular iteration has a convergent point, P star C. I should also mention that PT is positive definite. For all T greater than, well, T greater than 0. Oh, I need to give you P0 as well, right? Have they mentioned what P0 is? P0 should be actually Q, M transpose QM. or rather P star 0. Oh wait, I missed a negative sign. There is a negative sign here, and this iteration seems to be running backwards, so I have P of t equals to 0. Okay, so you start with Pt equals to 0, you run this backward in time, this differential equation backward in time, and it turns out that maybe in that case, right, okay, so this condition will no longer hold true in that case, but what will hold true is P star 0 converges to P C star as capital T goes to infinity, because you're starting from capital T and going backward in time. So in that case, your P star 0, which is the matrix at time 0, that will converge to an optimal sort of value. And this equation is known as a Riccati equation. Okay, so this is your LQR. This is another way to get a linear controller as a function of matrices A, B, Q, M, and R. And as you can see, if you are changing your Q and R matrices, if you're changing your Q matrix and R matrix, then you have to run this on the device itself. And that's why you need to have microcontrollers to be able to run LQR type controllers. But this controller is also a linear controller. F is given by this expression. Although F now depends on T, so I guess F should be a function of T. So that's your LQR. I know that we didn't do the derivation for LQR because it requires me to introduce dynamic programming in the class, and that's not part of this syllabus, but it's part of other courses that some of you might have taken. It's taught in reinforcement learning as well, but not in the continuous time. So the theory is the same. The implementation for continuous time is slightly different from the one in discrete time. The discrete time is what I'm more familiar with and I use extensively. The continuous time is something that I've never used in my life. But it also gives you a linear policy that minimizes some performance index. And in the case of finite horizon problem, this linear policy is time varying. In the case of infinite horizon problem, you converge to a specific P star C, and then you use that, you construct F using that P star C, and then you get a time invariant feedback policy. So those are the things those are the ways to design controllers. In the next class, we are going to talk about observer design. So in the current class, the goal was to place the eigenvalues, place the eigenvectors, and come up with controllers. In the next class, I'll talk about dual systems and then apply some of these techniques to do the observer design. Okay, so observer design is I'm getting the stream of yt. I want to figure out what xt or x hat t is. I want to come up with some estimate of the state given all the observations and measurements that I'm making. So the controller design talks about controlling the system. Observer design talks about estimating the state of the system. And after we talk about observer design, then we combine the two and we talk about like the entire end-to-end control system design. So from measurement, you are estimating the state. From state, you are applying this feedback control law in order to compute the state update. And hopefully the overall system is going to be stable. And that's what the topic for investigation is going to be next week. Thank you so much, and I'll see you next week. Bye.